fundamental science until one can see there are interesting device perspective using physics and other interesting concepts. So what we will do with the lateral engineer, that means we can engineer material at the atomic scale. Lateral we can connect two different type of material besides that interface, and we can see very interesting physics evolving at the interface and their prospective application in light emitting diode at room temperature. If you go to low temperature, one can expect quantum emitter type feature one can also. So before going to that, our work involved mostly fabrication of this kind of lateral engineered structure. We can create like PN junction using simple CVD method. We can definitely control the number of width. And second recent work I will show it at the end. So you can start to different set of lateral heterostructures. You can see multiple exciton, phonon, and second harmonic generation modulation. How we can tune it using this combination of structure. Another important aspect is this material what will grow as directly grow as a P and N type semiconductor that give lot of opportunity to do lot of optoelectronic devices, because PN junction diodes are fundamental to many applications including LED, solar cell, photovoltaic, and laser. Many more can be expected from this kind of combining when probing in device geometry. I'll explore that. Just to show that kind of material can grow is selenide based, is all Raman PL mapping. You can see very well defined domains are present at the lateral interfaces, and one can control monolayer, one can control precisely bilayer, and one can get atomic interface less than a nanometer. So we can go up to sub nanometer resolved interface which is not accessible in 3D semiconductor. So we can see that well-defined structure can grow, and from device point of view, one can make suppose MOS to WSC2, so we can contact electrode, you can make FET, and by applying backgate field, one can locally populate. Since these are spatially separate, one can spatially modulate carrier in one domain precisely. So by applying gate voltage, one can populate more electron in the dope. It's called electrostatic doping, make N-type, or WH which is indicating a P-type. That indicates one can indeed grow PN junction diode directly using these CVD methods. And later on I will show you what are the prospective applications of these things. What are the future of these 2D materials? So we know that 2D material mobility is limited. It's not like conventional gallium arsenide or this kind. There is high mobility material. For 2D material, electrons is though carrier dominated. So can we, for photon we know that very high speed information can be processed. But can these two fields can be merged? Disadvantage of one aspect can be controlled by the other by combining the other aspect. No, because these two have different things. If you add some kind of heterostructure to different kind of material, then you can form kind of hybrid. So we can use the excitons as polariton using the concept of light and matter interaction to control such materials or harvest some interesting physics by using this concept. For that, what would be ideal material is more on lateral heterostructure, where we can precisely modulate the carrier on demand, and we can create the formation of excitons or different kind of phases very precisely. Unlike in 3D 2D bulk, 2D in bulk in the sense pure form of material, where we cannot control excitons. Those excitons are very exciting, but we cannot control them. Then it limits the application of this kind of structure for practical devices. So with that, lateral heterostructure, what I can show, there is a plethora of opportunity if to engineer to make quantum dot, single photon emitters, and it can give a very one-dimensional transport arrays. And we can recently show that we can form a 1D quantum system using this kind of structures. So what is the bigger things to probe here is when two 2D materials are connecting very precisely. So what happens, and if they are of different polarity, one is dominated by electron and the hole. So electron is sitting one side, hole is sitting other side. If the interface is very sharp, then electron, there is a strong Coulombic interaction between the electron and hole that should stabilize the excitons, or they should not recombine. They should not recombine. In that case, because of the p-n junction, there is a strong inbuilt field present exactly at the interface because it's a p-n junction. So one is there is an inbuilt field which try to destabilize, and Coulombic interaction that try to stabilize the system. So as a result, there is a balance between these two systems to measure it. What is the condition? Minimum condition is this interface have to be very sharp so that electron hole in the wave function can overlap, interact, and second thing, the band offset must be more than 100 millielectron volt so that this 1D excitonic dipole can exist or can be probed. But whenever I asked to many collaborators long back, so can we measure it? Because there is very interesting 1D physics platform is present at the interface. But many people will be skeptical to measure it. It is because if you look at your typical laser or Raman microscope, people use 1 micron beam and the interface is 1 nanometer. It is almost 1,000 times weaker than one can expect. So the quantum yield for this to measure this exciton will be relatively very poor. So to measure that, so what one need is very atomically sharp interface. It is very hard to achieve this, but rather we could now get this kind of high quality lateral interface, which is very less than a nanometer shift from this WSC2 to MOSC2 domain. And we have a potential offset by Kelvin probe, which is more than 200 millivolt. So in that ideal condition, now we can able to see some interesting things. And how we know that why lateral interface will help me is our recent paper where we can try to, if you have a diffuse interface or sharp interface, one can see that the band offset, because again another to note it, when MOSC2, WSO laterally connecting, you are creating a type 2 band alignment, which is very useful for exciton or photovoltaic applications. So here, when you have a type 2 alignment, when you have interface is very sharp, then there is strong interaction between the two systems. That bring the band offset closer is minimum. And if you have a diffuse interface, there is a gradual change in the evolution of the valence band from MOSC2 to WS2. The offset is larger. So in this case, one will not expect any interface exciton. However, in this sharp exciton, we can able to see it. And indeed, we can able to see this in this case. Suppose you can see MOS to WS2 interface is 1 nanometer, where ideally, theoretically, one can see hole is confined in the WS2 and electrons confined in the MOS2, one can see this charge transfer exciton at the interface, where the electron function can overlap and create a dipolar excitons. So if you look at this, is a large lateral heterostructure. So in the middle region is MOSC2, outside is WSC2, and the dotted line is the interface, and we can get a large emissions, which are the interface exciton. If you look at the pure MOSC2, we can get very high quality excitons and trion emission. There is no defect band in the MOSC2 where away from the interface, but exactly at the interface. So all the excitonic peaks are suppressed. However, the 1D exciton peaks are super bright exactly at the interface. So it is not about one dot. You cannot say that it's from defect or all this. It is coming overall whole across the interfaces. Okay. So and you can see the quantum yield is suddenly brighter. How it is possible? Just a 1 nanometer line width of the junction is giving more brighter exciton than the pure phases. So it must be some kind of, again, is a second step we are trying to understand whether there is exciton funneling to happening at the interface. So because of this strong potential is exist, all excitons are going and trapping and giving rise to the 1D exciton. And surprisingly, this 1D excitons giving long lifetime is almost 15 nanosecond. And since what is the proof of it is a 1D, because you shine a light, you observe how the exciton diffuse. If it is indeed confined at the 1D interface, it should diffuse one direction now. So you can see that there is a asymmetric in the excitonic diffusion map, where you can see that exciton preferential diffuse along the one directions as compared to the across the interface. And from that, with the time scale, we can able to calculate the exciton mobility of more than 1200. if you look at the electronic mobility in this kind of system, it is roughly 10 to 20, but here we can get several order higher mobility of the exciter in these things. And this is more controlled because you can guide them in one direction. So then, what is more exciting, it comes out. So when you are shining light, if there are a lot of exciting states, it will give a usual PLP give a broad photoluminescence. But here, when you reduce the light intensity, so then you can see that the ladder of peaks originating across the interface, it's still brighter than the original molybdenum peaks. And if you separate the energy, they are all, their energy is separated by 7.2 million volt, and these are also which truly one can see a center of mass frame like 1D confinement potential. So one can realize a truly 1D quantum wire which is sitting just at the interface. So and one can measure this like textbook type of knowledge quantum well. One can see very precisely, not like dilute refrigerators, simple at 4K. Typical, and since the energy is higher, one can expect at higher temperature one can should able to see this on the excitons. Okay, so what more we can do is how to measure the dipole length of this. One can use a split gauge, and when you are applying enough field, planar field to the interface, then you can see the start shift from negative implant field as function of implant field, and the energy is all 5 states of these excitons are shifting, blue shifting as a function of field, and from that one can calculate the dipole length. So which is roughly coming largest dipole 2.2 nanometer. A 2.2 nanometer dipole is sitting there, and the confinement potential one can extract from the harmonic potential well. So 2.8. A 2.8 nanometer quantum well is sitting at the interface, and all these states are 5 exciton states are present. Okay, so that was very super exciting. Then we thought of what is the next plan is, since these are truly quantum wells, independent states, whether these all can be give single photon emitters, because this will be ideal for single photon states. So our next is follow-up paper. We just we got it. So what if we know that the exciton is moving around one direction. If you apply top gate field, then you can confine that exciton into quantum dot. That one can expect. Then you can expect, that confined quantum dot, again further you can tune the band and you can expect single photon emitter or this kind of state. But surprisingly, these are the finger gate as a function of very narrow, because you have to confine it. In order to get a quantum dot, you have to go down to very small dimension. So by using the finger gate, so this in interface exciton which is now sitting like that, now another vertical field, now we are confined. By applying gate field, we can see the sum of the exciton indeed. This confinement potential we can give like that, and this exciton step can be trapped. But what surprising, when we again as the typical PL, you can previous slide you see it, when you apply more brighter or more powerful laser, so you get a broad photon. You cannot separate these energy states. But now here from lower to higher power, when you increase the power, what you can see that the filling of the exciton states are shifting to blue states. Imagine you have the 5 exciton states. We expect when we are increasing the power, all the states will feel equal, and eventually it will give a bright photoluminescence. But when you are increasing the power, this shifting is happening and in the upward direction, and the higher energy states are saturating at a higher power. Again, eventually it is saturating. Usual PL, it's not saturated. That means it is going towards something strongly correlated region, where compressibility coming into picture, where all the dipoles are now becoming localized, and they don't allow additional any dipole to stack in that kind of system. How can you validate this compressibility and whether it is going to a strongly correlated region? So again, G2 can give another measure. So thermal light, or it's a weakly correlated classical light. When we go to lasing and this kind of, we see that strongly the interaction correlation, and when we go to a strongly correlated, this is a localized case. So that can be used like correlated light, like single photon correlation, where one can see that is a classical light where is a laser, or if you have a quantum light, so you get G2 less than 1. So indeed, if you can see that confinement potential, so when you have very low light, 200 nanowatt, one could expect a single photon, but rather we will get G2 more than 1. But when you are decreasing or increasing the power, one could expect this value to increase, but it is switch overing from a classical to a non-classical light. So that indeed, again we are trying to understand it, more things are going on. So it is that why this kind of situation are occurring here, unless there is a strongly correlated regime is occurring and that confinement potential. So because of this is what further things are going on. Okay, now coming to, as I promised, I can show you how this a single platform can be connected to a multifunctional manner. One device, whether it can be work like a detector, emitter, and other aspects. So we do because since, as I told, we have PN junction, we can do a lot of photo detection. As Atikuru also mentioned, photo detector or photovoltaic one can PN junction is very good for that. And also electroluminescence, these are complementary. Either you shine a light, you extract the current, since there is inbuilt potential, it can be efficiently collect carrier, or if you have a PN junction, then you can selectively inject electron and hole, and if there is a depletion region, they recombine at that depletion region and emit a light, and we can create electroluminescence. And we can do CMOS logic, because since you have a PN junction, we can create complementary NMOS or PMOS and NMOS. We can combine, we can realize CMOS computing. And also we can do a lot of transistor, BJT rectifier, a lot of things can be realized single platform, and indeed we are doing that. So what is the key challenge, as I already mentioned? Okay, I'll skip that. So PN junction, there are fundamental understanding is lacking in this. So we all talk about PN junction. In bulk photovoltaic or bulk PN junction, there indeed, when P and N type semiconductor are sandwiched, there is a depletion region present at, which is several hundreds of nanometers. How about 2D material? They are already in the quantum limit. They are already in the 1 nanometer limit. Whether there is no effective carrier diffusion. Carrier already confined to individual domain. Whether there is any indeed depletion region. So as per the previous, it is like PN junction when it stacked to 2D material, carrier can be combined in a tunneling mediated process, because there is no drift or diffusion type process, because these are quantum layers. So this is indeed valid for vertical structure, but nothing available in lateral. When you are two specially connecting two different material, whether that depletion region is present, because unlike vertical structure, there is no covalent bonding. But lateral geometry, there is a covalent bonding. There is stitching between one and another two material. What exactly happened at the interface? When you have one side dominated by N and another side dominated by P, whether one can get a confinement and depletion region present at the interface. So why depletion region is important? One can see here, this is the fundamental building block of any electronics or optical material, because just by applying field, either one can apply lateral field by VD, source to there, to modulate the tune, the channel slope, or you are applying vertical field where you can electrostatically dope one material at a time. Okay, so indeed what you can see that when you have PN junction, you shine light over and they collect current accordingly. Okay. So then one can see that wherever there is a depletion region, you can get maximum current, not other region, because when you shine light in other part of the system away from interface, you're photoexciting, but electron whole lifetime is so short that they can recombine immediately, so you don't get any current. But when you have an interface, you can expect a maximum photo current from the exactly like the interface. Okay, so I just to understanding that what is more fantastic here is, since unlike conventional semiconductor where we cannot assess the interface, but here the interface we can see it, and we can control doping individually. That gives us that feeder. So that way, by allowing electrostatic doping, we can modulate are the interface junctions. So we can indeed shift the depletion region as depending on the type of doping. So for example, if you have a negative backgate voltage, so you are depleting depleting the MOST2 region and WH2 region whole are more active than electrons are like tortoise and rabbit. They are switching the side. So the whole are more mobile, they are coming to the electron other territory and are recombining. That means the depletion region is shifting towards the MOST. When you have a positive gate field and you are depleting the holes and electrons are more active, then electron go to the hole regime, then WSC to recombine. So that means, yeah, that give us very flexibility in tuning these interface junctions and junction potential. That give us a lot of tunability in photodetectivity. We can get a high responsivity photodetectivity. All these are skipping. We evaluated details of the device aspects. Okay. We can get very high detectivity in this kind of material, transit time or nanosecond. In this kind of, we can reach indeed high photoconductivity gain. So in similar concept in electroluminescence, one can see we can, again, since we can modulate this junction width, so one can tune this electroluminescence. There is a recombination happening in individual material. So what is required is correspond to that band gap. So that means we can tune these emitters spatially and spectrally. So that also can be possible by lateral geometry. We can see that by applying different gate regime, we can indeed tune this electroluminescence, their energy, emission, and intensity. So we can do this. This is not. It's a very fast switching process. It's again limited by the device measurement unit. We can less than 1 second. We can make the LED on and off. That gives us an opportunity. We can use digital logic because the gate voltage can be negative, positive, the 3 input, and EL can be 3 output. So that based on that one can do a logic operations. So terminal logic one can realize. We heard about binary logic, now we can realize terminal logic in this kind of concepts. We can do it. So avalanche effect is another important aspect. Now there is a buzzword about quantum technology. So avalanche effect is very important for creating high sensitive low light detections, even up to single photon. What is ideal is you have a PN junction. If you create reverse bias, you create huge background field. So the moment it is hit by a photon, so it can create avalanche of carrier. So that you can detect. That's how it can sense a low light or even a single photon. Okay. So in that case, in our lateral heterostructure, since these are spatially separated, it can create huge field. It can create at the interface. So one can see by backgate voltage, you can see sudden rise of current after threshold. And here by using these IDS by isaturations, we can get a multiplication factor of 10 to the power 5 because 2D materials have less dielectric coefficient as silicon. If you look at silicon, the dielectric is 6, and that's what is given a huge breakdown field. And in our very recent, we communicated, we can create, since we have NPN, PN junctions, we can create a bistable switching. You can imagine barely 1 nanometer thick sample. It can block voltage up to 180, which is really tremendous. So people believe that it will just burn out, but this, because it's a lateral geometry and it is addition to the high quality of the bilayer structure, it can hold a voltage of 180, and it can again suddenly avalanche effect. It happens, it suddenly go back and the sudden surge of current. You get, nowhere you can see that a huge ton of voltage suddenly after threshold voltage. Ideally, if you hold your device here and shine a single photon, it should able to detect a single photon in this kind of geometry. And then we calculate the avalanche multiplication factor, which is coming around 32, which is far better than any conventional semiconductor present, which is below 10, where in our lateral geometry we can get up to more than 30 avalanche multiplication index. So that means these are promising candidate for low light and high single photon level detection. Okay, I will skip. We have also a lot of work on the More. I will skip this part. already published. Then what is the advantage in, because we can set two different kind of material, we can bring these two platform into one. Unlike More system, what you see in the most of the literature, they will couple of micron. But here, we have developed a method where we can pick up all CBD grown big lab, more than 50 micron sample, and they have a multiple platform. So we can create multi-More network of structures, where you can probe phonons, SSG, exciton, and we can understand many more physics out of it, how all these fields are, how anomalous SSG is modifying this kind of case. Okay. So with APS, we can able to validate what are the underlying physics behind it. Okay. Oh, I will skip rather all this in future. I can show. Oh, in the last, what is that? Is a one material platform where we can do detections, where we can do emissions, and we can do computations and logical operations. And if you do at room temperature, they can use as a normal electronics. If you go down to 4K, and you can use same device as a quantum device for single photon avalanche detection, all this. With that, I summarize that we can really have a very interesting 1D quantum system using these 2D materials, and we can have future probably application for electronics, optics, and quantum devices. There are plethora of opportunity, of course, and these are my collaborators, device work, where students go travel and work in Mainz lab, and some of the recent quantum with Puneet, and also I thanks and also support from National Quantum Mission recently, and IONP support for device fabrication. Thank you all.
One or two short questions.
So I have a question on your second order correlation data.
Okay.
So what is the depth of the exciton potential underneath the gate? Because if you are increasing your power, then you're kind of dumping more excitons into the system. And so these excitons should start repelling each other. Because your tooth in the third one is dipole-dipole repulsion.
Yeah.
So I was just trying to understand, why are you claiming that, these are correlated states in that dot? Is it possible that because I see a dip in the G2, so is it possible that you are just kind of going with fewer excitons because they will kind of this case will just kick each other out?
No, what in typical pure, when there is no electrode, we have done that several power. You go for more microwatt level power, but we observe the usual process. But when trying to confine only that region, these anomalous things happen. And there are theory behind it, in the details are there in that archive. So they validated why in that particular field dependent process, strongly confining this correlation happening. We can discuss.
Nice work. Yeah, just one thing. So the depletion layer, what is the typical size of the depletion layer? Because at one point you showed some, I think, KPH and beta, where the potential is changed.
It is 200 plus 200 volt, millivolt.
No, the width.
Width is 50 to 100 to 200 nanometer around.
Okay, so these excitons that you're saying, like 2 nanometer, they are residing in these
depletion. Yeah, within that. That's why they're stabilizing somehow.
So within the depletion.
Yeah, within the depletion. Yeah. That's what otherwise they will destabilize. Again, that code, how exactly is happening, why they are limiting. So again, further studies are going on.
I just have a quick question. What is the lowest intensity of light that you can able to detect?
Oh, this is nano, hundreds of nanowatt.
Hundreds of nanowatts.
Yeah.
Okay, let's thank Prasanna for an excellent talk, and let's move on to please be here. There are two certificate talks, and master will be Dr. Sunita Kundu.